Welcome back. This is going to be the first of two video lectures covering section 4.2 of the text on the topic of determinants. Now, we saw how useful determinants were in helping us find the eigenvalues of 2 by 2 matrices, and the whole point of this section 4.2 is to develop the concept of determinant to higher order matrices with the hope of helping us find the eigenvalues of matrices of higher order, let's say 3 by 3, 4 by 4, etc. Okay, now I've taken this section 4.2 and I've broken it up into 5 different parts. Determinants of n by n matrices, the geometry of determinants, properties of determinants, determinants of elementary matrices, and finally, determinants and matrix operations. Now, what I want to do is cover these first two parts in this video lecture, and we'll take up these final 3 parts in a second video lecture. So let's begin with the determinants of n by n matrices. Now, when we first introduced the cross product back in chapter 1, we learned how to calculate the determinant of a 3 by 3 matrix. So let's go to the document camera and find the determinant of the matrix A. All right, let's work out the determinant of this 3 by 3 matrix. Now, you may recall that what we did back in chapter 1 when we were learning how to calculate cross products is we calculated determinants of 3 by 3 matrices by an expansion formula. So there we settled on this first row and we did the following algorithm. We took the first element in the first row, so we took 1, and then we multiplied it by the determinant of the 2 by 2 matrix that we obtained by deleting the first column and the first row. So we tacked on the determinant of this 2 by 2 submatrix. And then we took minus the second element in the first row. And then we multiplied by the 2 by 2 determinant, the determinant of the 2 by 2 matrix we obtained by deleting that second column and the first row. And so that's the determinant of the matrix with the first column 3 and 2, and the second column -5 and -2. And then we were back to a plus sign. We took the third element in the first row, -2, and multiplied it by the 2 by 2 determinant of the 2 by 2 matrix obtained by deleting that last column and the first row. So it's going to be the 2 by 2 matrix with elements 3, 4, and 2, 1. Okay, and now we've reduced the problem to calculating determinants of 2 by 2 matrices. So let's continue. We'll have 1 times, so this is going to be -8 plus 5. Then we'll have this -1 times -6 plus 10. And then finally, we'll have this -2 times 3 minus 8. Okay, now when we work these out, we'll have 1 times a -3, so -3. Then we're going to have 4 with a negative, so -4. And then finally, 3 minus 8 is -5 times -2 is plus 10. And so the net result is going to be 3. So the determinant of this matrix is 3. Now let's head back to the class notes and talk about this procedure in a little more detail. Now, in light of our calculation, the following definition seems natural. Let A be an n by n matrix. The minor associated with the element little aij, denoted by capital Aij, is the n-1 by n-1 submatrix of A obtained by deleting the ith row and the jth column of the matrix A. Now let's take a look at an example. In this example, we have a 4 by 4 matrix A, and we want to look at the minor associated with this element 4. Now this element 4 sits in row 2 and column 3 of A, so we want to look at the minor A sub 2, 3. And what do? We simply remove the second row and the third column from A, and the elements that remain form a 3 by 3 matrix, in this case the matrix A sub 2, 3 that we see over here. So That's the notion of a matrix minor. Now we can use the language of minors to help us write compact formulas for a determinant. Let's begin with the 3 by 3 case. So let A be a 3 by 3 matrix with generic elements Aij. Now, using the language of minors, we can write the determinant of A as simply little a11 times the determinant of the minor capital A11 minus little a12 times the determinant of the minor capital A12. Finally, plus a13 times the determinant of the minor capital A13. Now we should really think of this as a determinant formula for the matrix A obtained by expanding along the first row of the matrix A. Now there would be an equivalent formula for the determinant of the matrix A obtained by expanding, let's say, along the second row of A. And down here we would be seeing the obvious products. We'd be seeing A21 times the determinant of the minor capital A21. We would see A22 times the determinant of the minor capital A22. And down here in place of this, we would see little a23 times the determinant of the minor capital A23. Now, what would change is the signs associated with those products, because, in fact, the signs that we're seeing here in this expansion formula are really signs that are attached to the positions of these elements along the first row. This position has a positive sign associated with it. This position has a negative sign associated with it, and this position has a positive sign associated with it. So as we try to change our formula from an expansion along a first row to an expansion along a second row to an expansion along a third row, or for that matter, to an expansion along any one of these three columns, we're going to know what the products down here are going to look like. We just have to be attentive to what signs are attached to those products. So let's take a look at the signs that are attached to different positions within a square matrix. So each position in a square matrix has a sign attached to it. The sign in position ij, in other words, the sign that's attached to the position in row I and column j of the matrix, is -1 to the power of I plus j. And what that means is whenever I and j together combine to an even number, then that position is going to have a +1 or a positive sign attached to it. But when I and j together add up to an odd number, then that position will have a -1 or a minus sign attached to it. Now, here's the matrix of signs for a 4 by 4 matrix, and you can see that they form an obvious checkerboard pattern. Now, let's take a look at this position here, and let's understand why that has a minus sign attached to it. That is in row 2 in column 3 of the matrix, and since 2 plus 3 is 5, which is an odd number, that position has a negative sign attached to it. So these are the signs that are attached to the various positions within the 4 by 4 matrix, and you can extend this obviously to any square matrix and find its signs. You just have to notice that this upper right hand corner in the 1, 1 position will always be a positive sign, and the rest of them will fall into place as in a checkerboard pattern. Now with this in mind, let's think about a couple of different ways that we could write out the determinant of a 4 by 4 matrix. So let A be a generic 4 by 4 matrix with elements Aij. Now, let's look at a determinant formula that we obtain by expanding along the second row. So we're going to see products of the form A21 times the determinant of its minor. And that's going to have a negative sign associated with it because this 2, 1 position is going to be in a negative position. So that has a negative sign associated with it. And then we're going to have plus A22 times the determinant of its associated minor. And then we're back to a negative position, so minus A23 times the determinant of its associated minor. And then finally, we're back to the last element in row 2. We'll have A24 times the determinant of its associated minor. Okay, now let's look at an expansion along the third column. So let's work our way down this third column and expand and find the determinant formula along that third column. So we're going to see products of the form A13 times the determinant of its minor, and since 13 is in a positive position, that'll have a positive sign associated with it. And then we'll see the signs strictly alternate. Then we'll have minus A23, determinant of the minor, A33 times the determinant of its minor, and then finally minus A43 times the determinant of its associated minor. So we can calculate determinants by expanding along any row of our choice or any column of our choice, as long as we keep track of the associated signs. Now, these considerations lead us naturally to the concept of a cofactor. Let A be a square matrix. The ij cofactor of A is denoted by capital Cij. So this is the cofactor associated with row I and column J. And what is it? Well, it's the product of the sign associated with that position times the determinant of the associated minor. Now, for example, let's say we have this 3 by 3 matrix A, and we want to know what is the cofactor in row 2 in column 1. So what is capital C sub 2, 1? Well, first of all, we notice that 2, 1, since 2 plus 1 is 3, that's an odd position, so it's going to have a negative sign associated with it. And the minor A sub 2, 1 is obtained by taking out the second row and the first column. It's going to be the 2 by 2 submatrix with first row 2, 3, and second row 0, 1. The determinant of that 2 by 2 matrix is simply 2. And so the cofactor C21 is negative 2. Now, with this language of cofactors in place, we can now state the Laplace expansion theorem. And this theorem is just doing exactly what we already expressed. It's just now expressing it in the language of cofactors. Let's take a look at cofactor expansion along the ith row. And this is what is being expressed here in Formula 5. We're looking at calculating the determinant of A by expanding along the ith row. And what we see here in the formula is we're seeing the successive elements of the ith row of the matrix A being multiplied by the corresponding cofactor. And if we remember, the cofactor carries with it both the sign of the position and the determinant of the associated minor. So this is just the same formula that we saw before. It's just now being expressed in terms of cofactors. Likewise, there's a cofactor expansion for the determinant of A along, let's say, the jth column. And here in this formula, we see the successive elements of column J of the matrix A being multiplied by the corresponding cofactor. And once again, the cofactor is taking into account both the sign of the position and the determinant of the associated minor. So these are just representations. These are more or less the same formulas that we saw before when we looked at our 4 by 4 matrix. They're now just using the language of cofactors. All right, so let's put our formulas to use. Here are a pair of 4 by 4 matrices. One is called A and one is called T. Let's find the determinant of each matrix. Now, what's important here in both cases is to pick an advantageous row or an advantageous column along which to expand. So let's head over to the document camera and see if we can find some very efficient ways to calculate the determinant of A and the determinant of T. All right, welcome to the document camera. We're going to work out the determinants for a pair of 4 by 4 matrices. And you'll see that this involves quite a bit of calculation. So it helps before we begin to calculate to look for an advantageous row or column along which to expand. Now, here I can see various columns and rows that contain 2 zeros. I don't see any row or column that contains 3 zeros. So I'm going to pick one of these rows that contains 2 zeros. And in this case, I'm going to expand along row 3. Okay. Now I'm going to pick up expansions, additional terms here associated with this position 1 and this position 2. These positions containing the zeros will multiply their cofactors by 0, and so they will effectively be eliminated from the calculation. So I just have to carry along 2 terms, one associated with the position 1 and one associated with this position 2. Now, let's get the sign of this position. We start with a plus, minus, plus. That's a negative position, so we're going to have a negative sign times the value 1 that sits in that position now multiplied by the determinant of the minor associated with 1. So that's going to be the 3 by 3 matrix that has entries -7, 9, and 3, 2, 4, and 0, and 0, -6, and 0. All right, so what did we do? We took out the column and the row of that position, and we ended up with this 3 by 3 minor. We have to take the determinant of that. Okay, now, this is also going to be in a negative position, so we'll have a negative. We'll have 2. And now we need to multiply by the 3 by 3 minor associated with that position there. So again, we have to eliminate that column and a row, so we'll have -7, 3, and 9, 2, 0, and 4, and 0, 5, and -6. Okay, so we have 2 calculations still to do. Let's call this calculation 1. We have to get the determinant of this 3 by 3 matrix, and we'll call that one calculation 2. We have to get the determinant of that 3 by 3 matrix. Now, I think it's best to go off and do these as separate side calculations and then bring those values back up to the main calculation. So let's go down here. Let's do calculation 1. I need to get the determinant of the 3 by 3 matrix with first row -7, 9, and 3. Second row 2, 4, and 0, and third row 0, -6, and 0. And once again, let's look for an advantageous row or column along which to expand. And here we see a nice candidate. I like this column. It contains 2 zeros. Now when I expand along that column, I have to get the sign of this position correct. So that's going to be positive, negative, positive. So that's going to be a +3 times the 2 by 2 matrix. That's the determinant of the minor associated with that position 3. So that's going to be this little 2 by 2 down here. So 2, 4, 0, -6. Okay, now the determinant of this 2 by 2 can be calculated very easily. That's going to be -12 minus 0. So that's going to be 3 times the -12, or -36. So that's the value of this 3 by 3 determinant, -36. Now we have to calculate the determinant of this 3 by 3 matrix. That's calculation 2. So we have -7, 3, and 9, 2, 0, and 4, 0, 5, and -6. Now once again, we have to look for an advantageous row or column, and there are a couple of choices here. I'm just going to expand along that second row, take advantage of the 0 that's in this position here. Now once again, I have to get the sign of this position. That's going to be a negative position, so I'm going to start off with a negative sign attached to the value of 2, and I have to work out the minor that's associated with that position. So I take out that row and column, so we'll have 3 and 9. And then I'll have 5 and -6. Okay? I can skip that one because it's a 0. And then I'll be at this position, which again is a negative position. So I'll have a negative sign times the value of that entry, which is 4. And now I need to work out the 2 by 2 minor associated with that position. So that'll be -7 and 3, and 0 and 5. Okay? Now, let's work out each of these 2 by 2s. We'll have a -2. And here I'll have the -18 minus 45. -18 minus 45. And then I'll have a -4. So I'll say plus a -4 times the determinant of this 2 by 2 matrix. Now this one is just -35 minus 0, so -35. Okay, now when we work this out, we'll get 126, and then we'll have plus 140, and those together will give me 266. Okay, now we've done our two sub-calculations. Now we can go back into the mainstream of our calculation. Now what do we have? We have a -1 times this 3 by 3 determinant. Now we calculated that 3 by 3 determinant. That's a -36. And then we have plus a -2 times the determinant we calculated for that 3 by 3 matrix, and that was 266. Okay, so this is going to be, after it's all said and done, a -496. And so that's the value of this 4 by 4 determinant. And you can see that that's a lot of work. And this is going to be a nice plug for our next section, because I'll show you some methods whereby we can reduce this matrix, keep track of our row operations, and help us facilitate calculating determinants of these larger matrices. So once you get beyond 4 by 4, you get into 5 by 5 and 6 by 6, unless the matrix has a very special form. This method, this cofactor expansion method, can be very laborious still. Okay, now let's look at this 4 by 4 matrix here. Now this one has a very special form. This is what we would call an upper triangular matrix. All of the entries below this main diagonal are 0, and so this is considered upper triangular. And we'll see that the fact that this matrix is upper triangular gives us a fairly nice cofactor expansion. We'll see that if we expand, for instance, along this first column, we'll see that we can work out this determinant rather quickly. So let's pick on this first column and notice that there's only one element in this first column that's different from 0. So this is going to quickly boil down to, well, that's a positive position. So I'll have plus 1 times the 3 by 3 submatrix that I get by eliminating that row in that column. So this brings us down to -2, 5, 13, 0, 3, and 3, 0, 0, and -1. Now what we notice is that the matrix that we're left with is itself upper triangular. So by picking this first column to expand along, I'm getting another upper triangular matrix. And so what we're going to do, of course, is just repeat the same process. It worked once, it's going to work again. Let's expand along this first column. So what we're going to get is a plus 1. And now we're going to have a -2 times the determinant of the minor that's associated with that position. So that's going to be 3, 3, 0, and -1. Okay. And now the rest of this calculation is easy because I can have a 2 by 2 matrix. So I'm going to have the 3 times the -1 and the 0 times the 3. So that's just 3 times the -1. So we have a plus sign, a 1, a -2, a 3, and a -1. And when we work that out, we're going to get 6. Now what's special here, and we're going to want to make note of this, this is a triangular matrix, an upper triangular matrix. The same phenomenon would hold if we had a lower triangular matrix. We could easily expand along that first row if this were a lower triangular matrix. But the point is, because it's a triangular matrix, what we see is by the time we're finished calculating our determinant, what we actually have is just the products of these diagonal entries. And so when we see a triangular matrix like this, we can easily calculate the determinant by simply multiplying the products, multiplying the diagonal entries of that triangular matrix. So that's a special feature of a triangular matrix that we're going to want to make note of. So we can get to a point where the determinant calculation is actually rather simple. So this one has determinant 6. Let's head back to the class notes. Now, Theorem 4.2 just generalizes what we saw in our example with our matrix T. The determinant of a triangular matrix is the product of the entries on its main diagonal. So if we wanted to think of A as a matrix with generic entries Aij, if that's a triangular matrix, then the determinant of A is simply the product A11 times A22 on down to ANN. You simply work your way along that main diagonal of the matrix A, and as long as the matrix is triangular, that product will be the determinant of the matrix A. Our next topic is the geometry of determinants. It turns out that determinants are useful for calculating certain areas and volumes. Let's take a look at an example in the plane. So let U and V be vectors in the plane. Let's say for the sake of argument that U has components U1 and U2, and V has components V1 and V2. Now, we know as long as U and V are not themselves parallel, that they determine a parallelogram. What we want to do is compute the area of that parallelogram, and it turns out that we can easily compute this area using determinants. So let A be the matrix that we get by either feeding in U and V as rows or as columns. It doesn't matter. Then the area of the parallelogram determined by U and V is simply the absolute value of the determinant of the matrix A. Now, with a little bit of thought, we can see where this formula comes from. If U and V were vectors in three-dimensional space, we could compute the area of this parallelogram through the cross product. We could simply take U cross V and then compute its length. That would give us the area of this parallelogram. So the first thing we need to do if we're trying to get to this formula is to take the vectors U and V and embed them in three-dimensional space. And we can simply do that by adding on a trivial third component. So by extending U and V into three-dimensional space, we now have access to the cross product. Now, when we want to take the cross product of U and V, we're simply going to feed our standard unit vectors into the first row, the components of U into the second row, and the components of V into the third row. And we're going to compute formally the determinant of this matrix. Now, because of the zeros in these two positions here, when I look at the parts that correspond to the directions E1 and E2, they will both be 0. So all of our cross product is going to be in the direction of E3, and it's going to be scaled by the determinant of the minor that's associated with that position E3. Now, if we stare at that, this is just the matrix that we referred to as A on the previous slide. So this has got the components of U in row 1 and the components of V in row 2. Now, the length of this cross product is going to be the absolute value of this scalar times the length of E3. But E3 is a standard unit vector, so it has length 1. So the length of this cross product, U cross V, is simply the absolute value of the determinant of this matrix A. And so this is what gives us our formula for the area of the parallelogram in the plane determined by the vectors U and V. It's simply the absolute value of the determinant of that matrix. Now let's study this through the lens of transformations. I've set up a matrix A here with entries 2, 1, 1, 4. Now we know the meaning of that first column. If we think of A as a transformation, we know that 2, 1 is the image of the standard unit vector E1. And we can see that here. I've used the vector 1, 0 as my input vector, and I can see that its image under the matrix A is the vector with components 2 and 1. Likewise, this column here, the second column, 1, 4, that's the image under this matrix of the standard unit vector E2, the vector with components 0 and 1. Its image under the matrix is 1, 4. Now, if we look over here, we can see that those two output vectors, 2, 1 and 1, 4, are determining a parallelogram. And that parallelogram is the image under the transformation A of this unit square. So this little unit square over here is being transformed into this parallelogram over here in the image space. Now here's the important connection that we're making. By calculating the determinant of this matrix, right, we're getting in this case 8 minus 1 or 7. We can see that this parallelogram over here contains 7 units of area, whereas the unit square over here contains a single unit of area. So what we're seeing here is that as we apply this transformation, it's stretching space and it's expanding areas by a factor of 7. Each little piece of area over here is being expanded by a factor of 7 through this transformation. So that's a lens through which we can use this determinant calculation. We can see when we look at a transformation and its associated matrix, we can see how much it's expanding space. In this case, space is being stretched and expanded by a factor of 7, and that's the determinant of the matrix associated with the transformation. Now there's a higher dimensional analog of our theorem about areas. So in this setting, let U, V, and W be some vectors in R3. Now what we want to do is we want to calculate the volume of the parallelepiped determined by the vectors U, V, and W. And it turns out we can simply kind of do what we did before. We can take the vectors U, V, and W and either feed them in to a matrix A as its rows, or we can feed them into the matrix A as its columns. But it turns out that the volume of the parallelepiped in R3 determined by U, V, and W is given by the absolute value of the determinant of A. And with that, that brings a close to this first part of this video lecture on section 4.2. So join me for the second half of the video lecture on section 4.2, where we take up further properties of the determinant. Until then, take care. Bye-bye.